So, hello everybody. We're happy to have Guy Blachar of Bar-Ilan University, who's going to talk about semi-associative algebras over a field.
Yeah, okay, so thank you very much. I'd like to thank the organizers for the opportunity to be here. Yeah, so I'm going to talk about this, semi-associative algebras. This is a joint work with Darrell Haile, Eliyahu Matzri, Edan Rein, and Uzi Vishne. Now, feel free to stop me at any moment if there are questions along the way. I'll try to make it self-contained as much as possible. Um, yeah, so, and maybe before we start, I'll say that some of you might have heard the excellent talk of Suzanne Pamplun a bit more than a year ago. I will not assume that you remember anything. In this talk, she also mentioned this work, so I'll start fresh. Okay, so let's start talking about semi-associative algebras. Basically, the goal that we have in mind is to study, is to understand better what are non-associative central simple algebras. So we want to understand what are non-associative central simple algebras. So, so for me, so central means that the center equals the base field. So we're working over some fixed field. So we have F is some field that we fix at the beginning. So central means that the center of the algebra just equals to the field. Simple means, of course, no ideals. And you want to study a non-associative generalization of the central simple algebras, which appear very naturally in the study of associative algebras, to the non-associative realm. Somehow trying to see whether, when we think of these associative algebras in the non-associative world, we get some new tools to understand better the original algebras we start with. Um, so there are several ways that we can try to generalize this. Of course, we can just say, okay, let's look at, as we said, the non-associative central simple algebras. And the basic problem, and the main problem is that while this class has some nice properties, it's too large. Basically, we expect many non-associative algebras to be central and simple, and we don't have any kind of structure theory for them. It's very, at least it seems very far away. Uh, so instead of going to all central simple algebras, what we really want is to try to find some smaller class that we can deal with. So we want to start with something, some stronger assumptions on the algebra. We might, and then somehow try to gain an analog of the associative theory in the non-associative world. Um, so I will mention that, that there were other attempts to study these kind of algebras. So maybe just some history or background. Um, so for example, there have been studies of non-associative quaternion algebras, which I will mention later and give the definitions. So non-associative quaternion algebras were studied in several papers, for instance, by Dixon, also by Albert and Waterhouse. Uh, so all of them studied the non-associative quaternion algebras in depth, understanding what kind of behaviors we can expect, when are they associative, non-associative, in terms of what is their structure theory. So this is one type of generalization that came before. And also in recent years, there were other work trying to understand better non-associative cyclic algebras in works of Steele and Pamplon, and also non-associative cross products, and so forth. Also, there were petite algebras, and there are several classes of these algebras that have been studied in the past and trying to give these kind of non-associative analogs to non-constructions from the associative world. So in our work, instead of going by these examples, we want to go in the other direction. We want to try to find some structural assumptions that will somehow enable us to capture all of these examples together and trying to give this theory in some kind of look, another viewpoint to study it. So so let's start writing things. Let's start going towards the definition. So all of the algebras in this talk are assumed to be unital, and finite dimensional over the base field F, I do not assume, of course, they are associative, otherwise I wouldn't come to the seminar. But we assume they might be non-associative, they might be associative. So let's take such an algebra A. See, this is an F algebra. So let's recall some definitions that we'll use. One definition that we'll recall is the nucleus. The nucleus of the algebra is the set of elements that associate with all other elements. So the nucleus of the algebra is all of the elements in the algebra, such that if we take the associator, no matter where we place this element x, it always vanishes. X, this is 0, where these brackets means a, b, c, minus a, b, c, just the standard associator. So the nucleus is the set of elements that associate with everything, and this is an associative subalgebra of A. So of course it contains the base field F, but in general could be larger. And the center of the algebra, if we talk about non-associative algebras, we assume to be all of the elements in the nucleus that commute with any other element. So here right here, as you probably know, we consider only elements in the nucleus. And again, an algebra is central, and we will focus on central, say F central, if its center equals F. So now, when studying associative central simple algebras, one very useful tool that we have is the use of maximal subfields. So we can take such a division algebra or central simple algebra. We take a maximal subfield of the algebra, and this is used in the associative theory to study many properties of the algebra, understanding when it splits, understanding some kind of, if it is Galois, and understanding some kind of description of the algebra in terms of the maximal subfield. And this is a very useful and powerful tool that we have in the associative theory. So our philosophy in this definition that I'll give now is to try to imitate this, and semi-associative algebras will be non-associative algebras that have a nice maximal subfield in this sense. So we will assume that we have this subfield, and this subfield will lie in the nucleus of the algebra. So basically, we are interested in algebras with nucleus which is large enough in this sense, contains this kind of maximal subfield. And once we have this maximal subfield, we have somewhere to start from. We have this powerful tool, and from that we'll see how we can get very detailed structured theory of these algebras. So let's give the definition of. Let's begin with the definition of semi-associative algebras. It will look like it might look like a long definition, but eventually most of it will just be standard things. So let A be an F central algebra. I'll assume the algebras are all central from now on, unless otherwise stated. So maybe I'll omit it from now. And we assume, okay, so we have this central algebra, of course, finite dimensional, and we assume that we have in the nucleus an étale subalgebra. So be an étale subalgebra. So étale subalgebra, there are several definitions of it, but maybe the easy way to think of it is a finite direct product of fields. So basically, we have a finite direct product of fields. They all contain F, but field extensions of F, they can be larger than F. So K can be just a field. K can be a direct product of copies of F, or copies of F and some extensions of F. So we have this subalgebra. We assume it to be in the nucleus, which is really important, because once K is in the nucleus, K acts. K acts on A by defining just the usual K times A is just K, when K in an element of K acts on an element of A with just multiplication, but actually, because K lies in the nucleus, we can actually get a better action. It's not just K acts on the algebra, also the tensor product of K with itself acts on the algebra by taking, if we take k times k prime acting on A, is ka times k prime. So this gives us immediately a structure of a k tensor k module. So A is a k tensor k module, and we say that A is semi-associative if this module, well, we have several ways to phrase it. Let's say semi-associative if A is a minimally faithful k tensor k module. K tensor k module. Well, minimally faithful means that it has no submodules or quotients which are faithful, is k tensor k modules. So in this sense, it is the smallest it can be. It is faithful, but you cannot decrease it in some way. You cannot take any substructure or quotient to get a faithful module. Now, because K is an étale algebra, we can actually get an equivalent characterization is that A is a cyclic and faithful K tensor K module under this action, of course. So we're working with this action, and semi-associative basically means that we have this subfield or this étale subalgebra that acts minimally faithfully on the algebra or in a cyclic and faithful way. Okay, so that's the definition. These are the algebras that we're working with, and we should think of K as the role of maximal subfields in the associative theory. Now, you can definitely think of K as a field. It doesn't really, for most of, you can think of K as either as a field or as copies of F. For most of what we say, you can just think of these two cases, but we'll explain each of them in its time. Okay, so these are semi-associative algebras. Before giving examples, maybe I'll say some remarks. We'll give some remarks about the definition. Well, first you can see that this class of semi-associative algebras is not defined as a variety of algebras in the sense that it doesn't come from a set of equations or identities that we assume the algebra satisfies, but rather some more structural thing inside. So it doesn't form a variety of algebras. Nevertheless, we can still talk about the structure of these algebras. Now, perhaps the first thing that we can ask, okay, how much does it depend on K? Apparently, it doesn't. So actually, being semi-associative is independent of K in the sense that if you have two étale subalgebras in the nucleus, is independent of K. If you have two maximal étale subalgebras in the nucleus, so maximal in the usual sense, then A will be semi-associative with respect to one of them, if and only if it will be semi-associative with respect to the other one. So while K seems to play a very major role in the definition, if the nucleus happens to be large enough and contains several maximal étale subalgebras, then eventually you can remove this dependency on K. And maybe just to see the first advantage of this definition, well, since A is cyclic and faithful as K tensor K module, let's just see one application of this. Well, A is cyclic as a module means that there is some V such that A equals KVK. This is just being cyclic. There is some vector that under the action of K tensor K generates the whole algebra. Okay, so that's being cyclic, but because A is faithful, by faithfulness, that also means that this action of K tensor K on V is faithful, so the dimension of A over F is the square of the dimension of K over F. Basically showing that the dimension of any semi-associative algebra is the square, which is classical thing for associative central simple algebras, and here just comes from this definition, from this maximal étale subalgebra. So when we talk about maximal étale subalgebras of the nucleus, these are the étale subalgebras such that the dimension is the square of the dimension of the algebra, and we actually call this square of the dimension is what we call the degree of the algebra, imitating again from the, sorry, degree of the algebra, imitating again the associative world. So algebras of degree 1 is just the field, algebra of degree 2 is something of dimension 4, and so forth. So we have this, the dimension is the square of the degree. So let's give some examples of semi-associative algebras. So the first example, of course, is that any associative central simple algebra. So associative central simple algebras are semi-associative. This follows from a theorem of Jacobson in the, oh, wow, now we forgot. Cathernet and Jacobson, yeah, just these three. They always contain this étale subalgebra. So that's one example. The second example is basically just mentioning the examples I talked about before. So for example, non-associative quaternions. So what are non-associative quaternions? Suppose that we have some quadratic extension. We have a quadratic extension in the, let's denote the Galois group of K over F just generated by sigma. Then in non-associative quaternion algebra, we look like, so it will be Q, which is K with KZ, where Z squared is some element B, which lies in K, and when you multiply Z by an element of K, just comes sigma of K times Z for any small k inside K. Right, so this is non-associative quaternion algebras. Non-associativity comes from, so if B lies in F and is non-zero, then Q is actually a central simple algebra. These are the associative quaternions. But if B actually lies in the field in this large free K, then Q is non-associative. K is not F. Then it's non-associative, and you can try to calculate the nucleus. That it will always be central, and actually it will be non-associative and semi-associative, in fact. So these are all semi-associative with respect to K, the K that we started with, which was, as we said already, a field. So we get non-associative quaternions. Maybe it's also good to just to highlight the case where B equals 0. When B equals 0, we get Q is an associative. So it will be an associative algebra, but non-simple algebra. So it will not be simple. However, it's still semi-associative. So this is a good place to say that semi-associativity does not assume simplicity. So in this sense, when I said that we want to generalize central simple algebras, we assume centrality for convenience. We don't assume that the algebras are simple. However, we could have just restricted to the case of simple algebras, and everything would just work well. Okay. So these are non-associative quaternions, and I'll also mention that very similarly you can define non-associative cyclic algebras and cross products, and you can find a natural generalization of these that also fall into the family of semi-associative algebras. So basically this family includes many different examples. Now, maybe another characterization of semi-associative algebras, before we'll also mention another characterization, is that A is semi-associative if and only if I take if B is some simple subalgebra of the nucleus. So we take a simple subalgebra with a separable center L is the center of B, so separable over F. then we have a natural map from B tensor B to the endomorphisms of A. Just B acts B acts on A just like K acts on A. This defines an endomorphism of A as an L tensor L algebra, and this map is an isomorphism of algebra. Isomorphism of algebras, and actually we can replace some by all. So if this holds for one, a simple subalgebra, it actually holds for all of them. So this gives us another way to think of semiassociative algebras, is those where the action of these simple subalgebras of the nucleus behaves in this sense. Okay, so this is the definition of semi-associative algebra. And these are a few examples that we should keep in mind. So we could definitely keep in mind just these quaternions. So just to recall, the main thing that we have is that we have this maximal étale subalgebra K. The A is a minimally faithful K tensor K module. That's the definition of semi-associative algebras. Okay, now we want to somehow find analogs or somehow understand how similar are these algebras to the associative algebras and which properties are common, which are not. So we know simplicity is nothing that is not exactly common. But one major example in the associative world are matrices. So if you take a matrix algebra over the field, they're always central and simple. So in this sense, it's very natural to try to understand, okay, so matrices are definitely semi-associative. Can we find other non-associative things that behave like matrices? And also, maybe I'll use green for the associative. If we make associative remarks. So if A is an F a central simple algebra and associative, then one thing that happens when we extend scalars for large enough field extensions, for example, for the algebraic closure of F, and of course we can also do it with a finite extension of F, then this new algebra turns out to be isomorphic to a matrix algebra over the field. This is one way to see why the dimension is a square. When you extend scalars to the algebraic closure, it has to be matrix.
It's over F bar, right?
Over F
And
bar.
over
Yes.
F bar.
Yeah, thank you. Yes, thank you. So if we extend scalars enough, we get matrix algebras over the field, over the new field, over the larger field. So it also makes sense to wonder whether we have some similar properties for our algebras. So we start with a semi-associative algebra, and we wonder when we extend scalars for a large enough field extension, do we get something that resembles matrices? And turns out that we indeed get. So these are what we call skew matrices. So what are skew matrices? So let n be some number, and let's assume that we have some tensor, if you want to think of it in this way. So we just have this subset of f just indexed by three indices I, j, k. We call these a skew set. So these are just elements of the field, and we will assume where we assume that the Cij and Cijj will all equal 1. So we just want these almost diagonal coefficients to be 1, but you can play with the other coefficients as you wish. And then we define the skew matrix algebra. We define the skew matrix algebra, which I'll denote M and F and C. So as a vector space, if I just want to think of it as vector space, it will be spanned over F just by things that resemble matrix units. So we have these EIJs that behave exactly, that look like matrix units. But what we do is we actually have a deformation in when we consider the multiplication. So we take the deformation of the classical matrix algebra. So EIJ times EKL. So we want to multiply these two matrix units. Well, as the usual case, we want J and K to be equal. to get something meaningful. But then instead of just writing, well, for associative matrices, I should have just written EIL, and and for our deformation, we add the EIJL. So this is the definition of skew matrix algebras. Basically, we add these coefficients in the multiplications, and this defines a non-associative algebra. This is what we call the skew matrix algebra. So as usual, for instance, right? So in other words, Eij times EKL is 0, right? If J is different than K, and otherwise this stuff. So just for example, if we choose all of theCijk to be equal 1, then what we get, these Q matrix algebras, let's just note it by 1, are just the classical matrices. So in this sense, it's very simple generalization. And if you wonder about okay, what can we say about these algebras? Well, just some properties. Well, they're all central, actually. So the sum of EII, actually, maybe I should begin the sum of EII just behaves like the identity element, and this follows because of our assumption, because of this assumption, the one's coefficient inside, then the sum of EII always equals 1. Actually, the center of these algebras is always F. These are always the scalar matrices, if you think of it just as matrices. So these are all central algebras. And if you think of the nucleus of these algebras, well, the nucleus of these algebras can vary. It really depends on the choice of C. But turns out no matter how you choose C, under these assumptions, we always have the diagonal subalgebra, the set of all diagonal matrices. Maybe just to avoid confusion, I'll write it as the sum of F EII. So this always lies in the nucleus. And in fact, if we think of the skew matrix algebras with respect to this K, with respect to this étale subalgebra, then basically skew matrix algebras are always semi-associative. So we have this minimal faithfulness for skew matrix algebras. So these are all semi-associative. I should mention that they are not always simple. Maybe I'll say that if all coefficients are chosen to be non-zero, then these algebras are simple. I'll discuss the ideas of these algebras maybe in a couple of minutes, but I will mention that as I mentioned that before, that the class of semi-associative algebra contains a non-associative, non-simple algebras, then also we can create non-simple skew matrix algebras. So also it has some similarities to classical matrices, but maybe some other there are some differences. Okay, so how do they appear? How do skew matrix algebras appear? Well, it turns out that if A is a K semi-associative, so here K semi-associative just means semi-associative with this K as a maximal étale subalgebra, and I take a field extension. This is a field extension that splits K. Splits K means that E tensor K, when I extend scalars to E, just isomorphic to just a direct product of copies of E. Then, when I take A and extend scalars to E, I get some skew matrix algebras for some C. So in this sense, again, if I manage to split K, to split the maximal étale subalgebra, I manage to split the whole algebra. This is what we'll call E splits A. So a field extension of F splits the algebra A if after extended scalars we get a skew matrix algebra. Right, and eventually under this identification, K will just be identified with the diagonal subalgebras, will just be identified with this subalgebra of the nucleus, if we really look at this isomorphism. Okay, so in some applications, so for instance, so some applications which are corollaries of this theorem maybe require a bit more work, but A is split. So split means that it's isomorphic to a skew matrix algebra, if and only if it actually contains in the nucleus this kind of diagonal there's a split étale subalgebra, just something f to the n, and here is the degree of A. So the square root of the dimension. So A split if and only if we can define enough idempotent in the nucleus. Enough idempotent is sum to 1. Right, so in this sense, if you want to understand which algebras are skew matrix algebras, it's enough to consider the nucleus of them and see whether there are enough idempotents. Also, if f is algebraically closed, then all semi-associative, no, all f semi-associative algebras are skew matrices. Skew matrix algebras. So in the associative theory, we know that over an algebraically closed field, the only central simple algebras are matrix algebras, and here in the non-associative world, all semi-associative algebras are the skew matrix algebras. So they really play the same role in this sense of matrix algebras in the associative world. We can also
Guy,
say that
can I stop you for a
yes.
second and just ask the question? I think you mentioned the notion of degree only in the context of cyclic non-associative semi-associative algebras.
So
Is it true? Or?
So maybe what I meant here is that A is a cyclic module. Since A is a
Okay.
cyclic module, then we can
Okay.
write A is just generated by some vector, and then because it's also faithful, the dimension is the square of the degree of K, the dimension of K.
Okay. So the degree is a notion that always exists.
Yeah, the degree is well defined for any semi-associative algebra.
Okay. Thank you.
Thank you for the question. Right. Okay, so returning to skew matrix algebras, so we know that if I manage to split K, I manage to split the whole algebra, and maybe we'll also mention something about the generic case in this sense. Some of the generic case, if we think of a generic semi-associative algebra in some vague meaning of generic, then we don't expect the nucleus to be very large. Actually, somehow maybe if in the generic case, we might expect the nucleus to be precisely K. Just okay, we force the nucleus to contain K, but in the generic case, we don't expect anything else to appear. So somehow in the generic case, we have the following, that E is an extension splits A if and only if it splits K. So this is something which is a bit different from the associative world. There are associative central simple algebras that we can split, we can extend scalars and get matrices even without splitting any maximal subfield. However, in the generic case somehow of semi-associative algebras, if the nucleus is just K, just this étale subalgebra, then to split the algebra, this precisely means splitting K, just because of the first application that we have. Okay. Other questions so far?
This holds for any field extension, so you're not assuming that the over F is algebraic or anything.
Yeah, it actually holds for anything, for any field extension. Any further questions so far? Okay. So let's delve a bit deeper into the structure of skew matrices. There is a lot to say about them, but maybe I'll just mention a few. So what can we say about structure of skew matrices? Well, as I said before, there are non-simple skew matrix algebras. So if you really want to understand the ideal structure, we need to know some facts about the ideals of these algebras. turns out that any ideal of skew matrix algebra is homogeneous in the sense that it is spanned by some matrix units. So there are possibly only finitely many ideals of these algebras, just because we need to choose some subsets of EIJs and check whether they span an ideal. But actually, it's not. It's even easier than that, because also the ideals only depend on the image of the coefficients Cij,k in, let's write it as f over the multiplicative group, in the sense that it only cares, we only care which coefficients are zero and which are non-zero. That's the only thing that determines the ideal structure. And actually, there is a relatively simple algorithm to decide simplicity. We can just we can actually associate some semigroup or some finite graph on the EIJs, and somehow, and there is a correspondence then between ideals of skew matrix algebras and the closed subsets in this, or ideals in the semigroup, closed subset in the graph. So basically, there is a simple way to determine for a given skew set Cij,k whether the algebra is simple or not. So for instance, if you know that Cij is non-zero, for instance, then it's just enough that these are non-zero to get that the algebra is simple. But this is not an if and only if. There are other choices of skew sets that also guarantee this algebra will be simple.
By
Now,
ideals, you mean two-sided ideals.
yes, two-sided ideals. And maybe I'll just mention, I'll mention this, I'll just say it out loud. There are, okay, so there are natural counterexamples to many things that work in the associative world and fail usually in the non-associative world. So a square of an ideal is not necessarily an ideal. In not every skew algebra, not every skew matrix algebra is semi-prime or prime or simple. So there are many different kinds of these skew matrix algebras. The ideal structure can look very different between them, but basically only depends on which coefficients are non-zero. So this is talking about ideals. Let's talk a bit more about the nucleus. So what can we say about the nucleus? The nucleus is also homogeneous. So it turns out that also the nucleus is homogeneous. And actually, if I want to check whether EIJ, whether something associates, so I only need to check products of the form EIJ, EJK, EKL. Maybe I should write it once, EJK, EKL. This translates just to an equation on the coefficients. So we just want Cijk, Cikl equals Cijl, Cjkl. So if we want to calculate the nucleus of the skew matrix algebra, what we want to see is whether when do these equations hold. We want to check that some EIJ lies in the nucleus. We want to see that these equations are hold, and also when we put EIJ in the middle or in the right position of this associator, so we get some kind of system of equations, and then the calculation of the nucleus for a given skew set is just very, very straightforward in this sense. Now, the nucleus, as I said, is an associative subalgebra of A. So, as an associative subalgebra, we can also ask, what's the structure of the nucleus? Is it central? Is it simple? Does it have a radical? And turns out that it might have a radical, but actually we can find a very explicit Wedderburn decomposition of the nucleus, in the sense that the nucleus of the skew matrix algebra is just given by some semi-simple part with a direct sum with the Jacobson radical of the nucleus. FC, where actually S is some direct sum of matrix algebras over F, like sum of matrix algebras over F, uh, whose sum of degrees is N. So actually, we also know much more. We know that the Jacobson radical of the nucleus, we know explicitly, it's just the span of all Eij such that Ciji is zero, and it might look non-symmetric, but actually it's equivalent to Cij is equals zero, and S is all of these in the nucleus. The Eij is in the nucleus that are either exactly looking. We look at all of the Eij's in the nucleus, and then we just want to see whether this central coefficient is zero or non-zero. This is precisely what dictates whether you lie here or the span of the Eij in the nucleus. Ciji is non-zero. And as we said, S is the direct sum of matrix algebras, and the Jacobson radical is just whatever remains. Okay. And actually, we said that any semi-associative algebra, when I extend scalars enough, becomes skew matrices. Actually, also the converse holds. So if let's say if E over F is a separable extension, then A is semi-associative if and only if if we extend scalars, then this is semi-associative. So basically, it also gives us a way. It shows that our class is closed under field extensions, under separable field extensions. So it's closed under field extensions and also closed from above under extensions of under forms in this sense, or forms-based separable extensions. Right. So in other words, if we combine what we said in the last 15 minutes, A is semi-associative if and only if I can extend scalars, there is a separable field extension where after scalar extension, I get skew matrix algebra over E. Right. So, and this is, of course, line E. Right, so this gives another characterization of semi-associative algebras, precisely as those that after some field extension we get skew matrix algebra. So again, very similar to the associative world. Okay. So in time that I've left, let's talk about some kind of attempt to define a Brauer group or Brauer monoid of these algebras, and then see what are its properties. So let's return to the associative remark. Let's just recall that the Brauer group of a field is defined as a set of all central simple algebras modulo and equivalence relation, we will basically remove matrices. So basically we said that A is equivalent to B if and only if when we take A and take a tensor product with matrix algebras, we get it's the same as B with some other matrix algebras. And that basically means that in the associative world, they have the same underlying division algebra. Now, in the non-associative world, we don't have the notion of underlying division algebra in general, not for every semi-associative algebra, but nevertheless, we can still just attempt to do the same. So let's define the Brauer monoid. And the Brauer monoid will be so the Brauer monoid, denoted by the semi-associative Brauer monoid of F, will be just the set of all F semi-associative algebras of all dimensions, a modulo and equivalence relation where two algebras are equivalent if and only if there are, okay, so let's say Mn, and also skew sets C and C prime, such that A tensor skew set A tensor M with C is isomorphic to B tensor skew, these new skew matrices. So basically, we use the same definition as in the associative case, but we replace matrices with skew matrices. Now, this becomes a monoid. Actually, the class of semi-associative algebras is a semi-associative algebras is closed under tensor product. That's just requires a small computation. And once we know that it's closed under tensor product, we get that this semi-associative Brauer monoid is a monoid, the commutative monoid. And also, it's not hard to see that actually the classical Brauer group of associative algebras actually is embedded inside this group. So actually, it actually, if this new equivalence relation only extends the classical one and doesn't add new equivalences between two non-equivalent associative algebras. So the classical Brauer group sits inside this, and everything is well defined. So we get this inclusion, and we can ask, okay, so this is a monoid in general. We can ask, okay, what are its subgroups? How do elements here look? Now, one very important tool in analyzing this monoid is what we call the semi-simple part of the nucleus. So important tool is what we denote by sigma of A, which is the semi-simple part of the nucleus of A. So we could take the nucleus of A, which is, as we said, an associative algebra, modulo the Jacobson radical of this nucleus. So basically means, we just, this is a semi-simple associative semi-simple algebra. And this is very useful in the analysis of this monoid. So why is it useful? First, as we said before, not in this language, but the semi-simple part of the nucleus of skew matrix algebras are just the direct sum of matrix algebras over F, right? And the sums of the degrees is n. So we understand how it behaves on matrix algebras. And actually, this sigma behaves well when it considers field extensions. So this is the field extension of sigma of A, and also respects a tensor product. So if you take tensor product of two algebras, this is just the tensor product of the semi-simple parts of A and B. So in this sense, this is very useful. It defines a homomorphism. This basically means that sigma defines a homomorphism from the Brauer semi-associative Brauer monoid to the class of all semi-simple algebras. Or maybe it's more accurate to say from all semi-associative algebras, just to not mix up things with equivalence relations. So this gives us some way to study the semi-associative algebras in terms of semi-simple associative algebras. Associative semi-simple algebras. Now, associative semi-simple algebras, as we know, all split as a direct sum of simple algebras. So these are, or maybe it's better to write decompose. They all decompose as a direct sum of simple algebras which we will refer to as the atoms of A. So the atoms of an algebra are just the simple components of its semi-simple part of its nucleus. And it turns out that studying the atoms of an algebra, of a semi-associative algebra, gives us a lot of information about the algebra itself. So in what sense? So we can actually think of, in this sense, 4 classes of semi-simple algebras. So one of them will be, okay, so in general, maybe, we can think of, let's think of all semi-associative algebras. Let's write it M. Semi is the class of all semi-associative algebras. Sigma of them is just all, are in general, all of the semi-simple algebras, actually separable algebras. They're all separable. So this is maybe the large class that we have, but we can restrict ourselves into smaller classes. So for instance, we can define what we call semi-central. And semi-central algebras are those where all atoms are central over F. So they're all a priori only simple algebras over F, but we can restrict to the class of semi-associative algebras where all atoms are F central. So so if we apply sigma, we get what we call the semi-central semi-simple algebras. And inside the semi-central algebras, we can find those we call the homogeneous, where all atoms are Brauer equivalent. So basically, in the sense of which we denote by S home, which basically these are all semi-simple algebras where all components have the same underlying division algebra. And inside this, we can just consider everything which is a direct sum of matrices, which here just, this is just skew matrices. And here this will correspond to all split semi-simple algebras. Now, the semi-associative monoid, semi-associative Brauer monoid is somehow the quotient of the semi-associative algebras modulo the skew matrices. And we can say some things about all of these classes. So for instance, if A is homogeneous, so all atoms, let's write the definitions, are Brauer equivalent to each other, then we have a Wedderburn type theorem. Then there is actually an associative division algebra D such that A will be isomorphic to D tensor with skew matrices. So if you know that all atoms have the same underlying division algebra, we can actually just take it out as a tensor product, and the remainder will be just a skew matrix algebra. So these algebras, some of the homogeneous algebras, modulo skew matrices, are precisely the classical Brauer group. So this is just the Brauer group of F. And you can actually say more. Actually, it turns out that the first part, this one, is actually another characterization of skew matrices. So if I have a semi-associative algebra and I know how to compute the semi-simple part of its nucleus, I can just, this is another way to see whether this algebra is a skew matrix algebra or not. So maybe I'll finish by mentioning the following theorem, that in fact, so we said that the Brauer group lies inside the semi-associative Brauer monoid, sits inside is the unique maximal subgroup of the monoid. So in other words, so in other words, if you look at all of the invertible elements inside the monoid, all of them come from associative algebras. So in this sense, this monoid doesn't contain new invertible elements. It also has many other nice properties. So for instance, it contains elements of infinite order. So it's no longer torsion, at least under some assumption on F. Maybe I should have mentioned that the Brauer group of an algebraically closed field is trivial. Just as we said before, all semi-associative algebras of an algebraically closed field are all skew matrices. So in general, this construction shows that if you want to be invertible, you have to really lie inside this homogeneous part. You have to lie inside the homogeneous part, and you cannot be anything in the middle. Yeah, and so this is some kind of let's say new class of non-associative algebras, somehow generalizing some ideas from the associative part. As you can see, there are many similarities. There are also differences. For instance, the monoid really looks different, but definitely I think that they share a lot of similarities with the associative central simple algebras. Um, yeah, and I think they'll end here. So thank you very much.
Are there any questions? So I actually wrote a bunch of questions, but I'll just ask a few. So you mentioned, you began by mentioning previous works of non-associative quaternion algebras. Do they coincide with this setting? Like, if you take a degree 2 semi-associative algebra in your setting, do you get the same quaternion algebras?
Yeah, so actually, if you have a actually, yeah, we can say more. This is this is only maybe a small part in the current work. That if you have a semi-associative algebra of degree 2, right, and you find this maximal étale subalgebra, which is Galois, then it actually becomes a quaternion algebra. Yes, you can actually, yeah, so algebras of degree 2 are quaternion algebras, basically.
So it does coincide with the previous definition that had existed.
Yeah, definitely.
Yes. And do you have any, like, when you talk about skew matrices, like, do you have any variants of determinant or trace or characteristic polynomial or anything that comes from linear algebra that you can copy and adapt?
So that's a good question. We try to think, for instance, when a skew matrix is invertible, and then you can find some kind of a criterion for when are they right invertible or left invertible. It comes from some sets of equations that really looks somehow resembles determinant, but not really. We haven't really pursued this direction much. This characteristic polynomials, or some other questions in this area. Definitely something interesting.
Because for central simple algebras, part of the good thing that you have is that each element has a reduced trace and a reduced norm, and you get them via this embedding into matrix
Yes.
algebras.
So this is something that we haven't really thought about actually.
So more work to be done.
Yeah.
Other questions? Okay, if not, let's thank the speaker again.
Thank you very much.